Hey there, creative coders! This is Benjamin D. Whiting, and welcome back to the Super Collider segment of Null-state's interactive digital art tutorial series. Last week we began our discussion of using open sound control to send data from the server back to the client. Now, the conclusion of client versus server-side programming, OSC responder functions. Now that we know how to get the server to talk to the client, what does that enable us to do? If you recall from the first part of the client versus server-side programming series, I mentioned that there are certain kinds of operations that the Super Collider client can accomplish but the server cannot. These include, but are not limited to, the handling of true conditional statements, the scheduling and spawning of synths, the operation of graphical user interfaces, and the execution of patterns, routines, and event streams. Furthermore, the client does not deal in data sampled at the control or audio rate, meaning it cannot do anything with EnvGen save compile synth-def code into machine language. Therefore, if one wanted to include the current mouse pointer position in a conditional statement, one would be out of luck on the client side, as the classes that track mouse and trackpad behavior are all control rate unit generators housed on the server. Let's say we wanted to write a program that spawns synths when a low-frequency noise generator reaches a certain threshold, but the synth that is spawned is dependent on the position of the mouse pointer. How would we go about this? First, let's boot SC synth, but before we do so, let's increase the amount of memory Super Collider allocates for the server. By default, the language reserves 8,192 kibibytes of system memory for SC synth, an amount that has remained unchanged since Super Collider 3.0 for Mac OS X in the old PowerPC days. This made sense in an age when even 1 gigabyte of RAM was considered luxurious, but now that most people have computers sporting 8 or 16 gigabytes of RAM, 8 megs seems awfully anemic and can lead to out-of-memory issues before too long. Luckily, changing this is as simple as executing one instruction of SC long code. This will increase the amount of RAM allocated to the server from 8 MB to 1 GB, more than enough to do virtually anything one wants to do in Super Collider. This is not a permanent change, however, and will need to be invoked each time a new Super Collider session is launched or the interpreter is rebooted. Now, we can boot the server as usual either through the menu or by invoking the following instruction. Despite having consistently used the menu option up until now, I prefer having explicit server boot instructions in my own code, and will adopt this practice for these tutorials from this point forward. Next, let's prototype the synths we're going to spawn, the first of which will be a short, percussive sound. For this, we'll use a class called Klank. As its documentation states, Klank is a bank of fixed frequency oscillators that can be used to simulate the resonant modes of an object. In other words, it offers a kind of basic physical modeling capability and is rather useful in simulating percussive sounds, particularly metallophones. Let's begin this synth-def by declaring our arguments. We'll start with a panning argument, appropriately named pan and set to 0, and an amplitude or amp argument with a default of 0.2. We'll next need to declare our variables. Just follow my lead. I'll explain what each of these is for as we proceed. Let's have the synth randomly determine the fundamental frequency of our sound. This can be accomplished via the rand class. Rand is the server-side equivalent of client-side rrand in that a lower and upper bound is set and a random float is returned from within those bounds. The main practical difference between capital rand and lowercase rrand is that rrand is run only when a function, in this case the synth-def, compiles, thus resulting in the initial random value remaining constant until the synth-def is recompiled. Rand with a capital R returns a new value each time the synth is instanced. Also, capital Rand always returns floats, while rrand can be set to return only integers by not including numbers after the decimal point. Next, we set an impulse that sounds once every 10 seconds to variable sig. This isn't ultimately what will be bussed out of our synth, but it is an important component of the final signal. Afterwards, we start setting the variables that we declared below sig. As Klank is a bank of resonators intended to construct complex sounds, It is capable of accepting more than one value for frequency, amplitude, and ring time, the latter being a measurement of the length of time it takes for the sound to decay by 60 decibels. With regard to our freaks variable, while we could simulate non-pitched percussion, let's instead stick with a sound that adheres to the natural series of harmonics. This is accomplished by initializing an array and using the .series class method to fill each slot with predetermined values. The first argument in .series is the number of index slots to include in the array. The second is a value from which to begin the arithmetic series, in our case, the random value generated and set to our freak variable. And the third is a value to be added to each slot, which for our purposes will also be freak. The result will be an array filled with the fundamental frequency plus the following 12 partials in the natural series of harmonics. Now, I'm liking the idea of having the amplitude of each partial be the reciprocal of the partial number itself. This ensures that the fundamental receives the most sonic activity, while each successive partial is proportionally quieter to the one before it. .series won't be of much help to us here. We'll instead need to use .fill and write our own function supplying the values. With .fill, each index number of the array is passed into the function as an argument. I like using the traditional I to represent the index number, but feel free to use any labeling you'd like. To keep things nice and neat, let's declare a new variable and call it partial. We need to deal in one-indexed values, as the reciprocal of 0, the first index, is an infinite value and will result in an unpleasant sonic surprise should you forget the step. We end this interior function by returning the reciprocal of the partial, accomplished through the .reciprocal method. Next, we need to assign ring times to each partial. This time I'm going to be lazy and simply fill an array with 13 random values between 0.1 and 2. We don't need to declare an argument for the index this time around, as it isn't relevant to the instruction enclosed in the function. We follow up by initializing an array containing the frequencies, amplitudes, and ring times generated in the previous instructions and setting it to our specs variable. But wait, you might be asking at this point, what's with this backwards apostrophe preceding the array? Why isn't Benjamin aware of this typo and fixing it yet? By now it should be obvious by the inclusion of this hypothetical quotation that such a keystroke was indeed intentional. This mark is actually a syntactical shortcut for setting up what's known as a reference to this array. It's not necessary to go into detail regarding what a reference is, but for our purposes it's sufficient to say that using a reference to an array rather than an array itself will prevent SuperCollider from expanding the resulting sonic output over a multi-channel field. This is important as A, we don't want to split up each partial that will make up the sound, and B, even if that were our goal, most of us probably do not have 13-channel sound systems with which to monitor the output. Next, we plug the specs into Klank.ar, using the impulse-based SIG as the so-called exciter signal. Normally, we'd end a synth-def with the instruction that produces the desired audible result, but we can't do that yet. Given our objective, we're going to be spawning multiple synths, and each one instanced will add a certain amount of unit generators and processing stress to the system. As things currently stand, if too many synths are created, they will eventually lead to the server overloading and crashing. This is because synths, with all of their constituent unit generators, remain active indefinitely by default, regardless of whether or not any signal is still audible. What we need to do is instruct the server to free the synth as soon as it stops sounding. That's where the DetectSilence class comes into play. DetectSilence analyzes the resulting signal and, upon its falling below a stated amplitude threshold for a specified period of time, some action is performed on the synth. We're going to keep its defaults as they are, but for the done action argument we'll include an instruction for the synth to free itself via done.freeSelf. Note, done.freeSelf can be represented simply by its assigned index 2. One may well more often than not encounter code that prefers the index number approach over explicit statement. However, for the purposes of this tutorial series, I find writing out the various done actions is much clearer than expecting you, our dear audience, to memorize a list of 15 actions. We'll finish this synth-def by returning the signal multiplied by amplitude. However, instead of simply returning a duplicated signal, we'll be a bit more sophisticated and properly pan the signal using the pan2 class. Pan2 is a UGen that acts as a two-channel equal power panner and can be used to place sonic events in a stereo field. Its second argument is what is used to position a sound, and it ranges from -1, hard left, to +1, or hard right. We'll plug in our pan argument, which we set to 0 by default, though potentially externally modulatable. Finally, let's use the .asDefName convenience method of function to generate our synthDef, and test it by setting the synth to interpreter variable x. But wait, there's more! As our goal is to have the user be able to choose which synths are spawned by the position of the mouse cursor on the screen, we'll need to concoct a new, distinct synthDef. We used Klank for our first, so it seems appropriate to use its counterpart Klang for the second. Klang is similar to Klank in that it's a useful tool for generating complex sounds. Where Klank consists of a bank of resonators, Klang is made up of a bank of sine wave oscillators. Instead of ring times, Klang expects initial phases in its specifications array. Where Klank is well suited for percussive sounds, Klang excels at producing sustained tones. For the sake of time and convenience, we'll keep the bulk of the synth the same as our previous, changing instead our rings variable to phases, and altering its Array.fill function so that it populates the array with random phases in between 0 and 0.99. We'll also set the amp to 0.1 since we'll be working with sustained tones this time around. As Klang does not depend on an exciter signal to operate, we can delete our impulse UGen as well. However, with the loss of ring times comes a problem. Since Klang does not feature inherent decay, it can quite happily continue producing sound ad infinitum. DetectSilence will be useless for the purposes of freeing the synth. What we need is a way to shape the sound ourselves, and that is where envelopes come in handy. Let's first add a new variable to our declaration list, calling it env. To this, we'll set an instance of the class EnvGen, short for envelope generator. As we're only using this UGen to shape the overall sound of the synth, the control rate class method will suffice. EnvGen's first argument is the envelope to be applied, usually satisfied by an instance of the env class. Since our Klank synth produces percussive sounds with sharp attacks, let's choose one of the smoothest envelopes to apply to our Klang synth, a sinusoidal envelope. Its argument is the number of seconds the sound will last, which we'll assign randomly between 2 and 10 seconds. Like DetectSilence, EnvGen supports a done action argument, which we'll similarly set to have the synth free itself upon completion of the envelope. We'll ignore EnvGen's other arguments for now. Finally, in the last instruction of the function, we'll append our new variable to the formula determining the audio signal to be returned, multiplying it by the signal and the amplitude argument. Let's now try out our new synth. Our next step is to construct our control synth, followed by its OSC func counterpart. For the former, we'll once again use an LF noise generator to perpetually generate our random numbers. We'll allow for its frequency to be modulatable this time and set its default rate to 5 cycles per second. We will also add a new variable to capture the state of the mouse cursor. Now, as we'll be sending both values to our OSC func, we have two options. We could set up two send trigs, have the first send a random number with an ID of 0, and the second our mouse data with an ID of 1. Easier to deal with would be to pack both values into an array and send that over in one instruction, but here we run into a big limitation of that class. One cannot send arrays using sendTrig. This is where the more versatile SendReply class shines. The first argument of SendReply is just like sendTrigs, the condition that sets the trigger. Instead of ID for the second argument, however, we can specify our own OSC path. This alone makes SendReply an attractive choice over SendTrig, even when simply sending trigger values out. Finally, we send our values packed into an array. Our final task is to construct our OSC func. Here is where we bridge server-side programming with client-side. We need the function to perform the following tasks. Collect the message sent by our ~spawn function along the path /spawn. Determine if the random number sent in any given message is greater than 0.5, and if so, determine where the mouse cursor is on the screen. If it's in the left half, spawn ~Klank, otherwise instance ~Klang. How we fulfill our function's first duty is clear. Make sure the path argument is set to /spawn. The second and third criteria are a little more complicated. Can you figure out what steps need to be taken to satisfy them? Feel free to pause the video for some time to think. If you answered using nested conditional statements, you'd be correct. Even though we're sending over an array of values, SendReply helpfully concatenates that array with its own instead of nesting it. Therefore, our random number will be placed into index 3 as expected, while our mouse values will be stored into index 4. Now, we could work with the message argument directly in our function, but for the sake of clarity, I think it's a better idea to declare descriptive variables and set each one to the relevant index of our OSC message. Next comes our nested conditionals. Since we don't want anything to happen unless the random number generated is above 0.5, we should set that as our exterior statement. If that condition is evaluated as true, then we should check to see on what side of the screen our mouse cursor is. Let's make it so that if the mouse is on the left side of the screen, ~Klank will be spawned, otherwise SuperCollider will output ~Klang. While one could technically use a case statement here, since we only have two possible outcomes, another if-then statement would work just fine. Returning to our exterior conditional, as we want nothing to happen if the random number is less than 0.5, we do not need to include an else function. Let's also add a bit of spatial interest by randomizing the pan of each new synth initiated. Since we're not programming the server here, we'll need to use client-side rrand, in addition to adding a decimal place so that floats our output, not integers. Otherwise, everything will only be panned hard left, hard center, or hard right. We conclude our OSC func with the path upon which it must listen, that being /spawn. Don't forget that, since it's a symbolic path, it must be enclosed within single quotes. This so happens to be one of those rare instances where one cannot use the / option for symbols, as a / cannot be followed immediately by a / for the conversion to happen. I suspect it's similar to dual equals signs not converting into binary op-UGens on the server. Now all that we have left to do is to evaluate the code we've written, and enjoy some nifty sounds. Don't forget to periodically alter the position of the mouse cursor to switch from outputting percussive sounds to longer, sustained textures. After 1 month and just as many weeks, we have reached the conclusion of our client versus server-side programming mini-series. I hope you have a clearer understanding now of the distinction between the two, and can approach working on your own projects with more confidence. If any questions remain, please feel free to ask them in the comments below, and I will get to them as soon as I can. By the way, not only are we now finished with our pentalogy, we have also reached the halfway point of the SuperCollider segment of our series. My, how time flies! I have some neat things planned for the remaining episodes, so please stay tuned, fellow creative coder. In the meantime, please don't forget to hit that like button and subscribe to this channel to show your support for more interactive digital music and art content from us at Null-state. Also, make sure to check out our Facebook page and webpage to stay up to date on all of our upcoming events, workshops, and concerts. The link is in the description below. See you next time!